The example I picked is a contract that allows somebody to sell tokens. So the idea is that if I own tokens, I can lock some of them in this contract, set a price, and then other people can buy it, and I get the money they paid for it. In the beginning, the seller, the person or party that wants to sell tokens, starts with an NFT. And it can be an arbitrary NFT, and it will just be used as before to identify the correct UTXO that contains the contract state. The first step is for the seller to lock his NFT at the script address of the smart contract we are about to write. And I call that TS here for token sale. So you create a transaction, submit a transaction that locks the NFT at this address. And as datum, we will use a simple integer, which indicates the price of the token. And this starts off as 0. There will be several operations that the seller can do. One of those is setting the price to a different value. And in order to do that, the seller needs to submit a transaction that has the current UTXO as input and the updated UTXO as output, where the datum has been changed to a different price. So in this example, the seller set the price to 6
Loveless per token.
Another thing the seller can do is actually lock some tokens in the contract. So in order to do that, he has to create yet another transaction that has as input again the contract, the UTXO locked at the contract, and a UTXO containing some tokens that the seller owns, and as output just the updated UTXO at the contract address, which now contains the provided tokens as well. So in this example, the seller provides 5 tokens to the contract. Now for somebody to buy tokens, there needs to be created a transaction by the buyer that as input, of course, again has this UTXO sitting at the TS script address
and the buying price in Loveless.
So if somebody wants to buy 2 tokens, you would create a transaction that has as input the
price, 12 Loveless,
and the UTXO at the TS script address, and then 2 outputs. One, the updated contract state, where now the tokens are taken out and the price has been added, and one output going to the buyer with the tokens he just bought. Finally, there must be a way for the seller to retrieve tokens and ADA. So in this example, if the seller after the sale wants to retrieve all the ADA and 1 token, he would create a transaction that again has the script UTXO as input, and then 2 outputs, one with the updated script UTXO, where now some tokens and some ADA have been retrieved, and one to himself with the retrieved funds. And of course, this diagram just shows one example. So the idea is that these operations can happen in any order. So the price can be set several times, tokens can be added, tokens can be bought, and funds can be withdrawn in arbitrary order. I have implemented this in this week's code folder. The module name is week8.tokensale. And the first definition here is called token sale. It's a type, and it's the parameter type, so it parameterizes a specific token sale. So it's a record type with 3 fields: the payment pub key hash of the seller, then an asset class called TS token, so that is the token being sold. And finally, something of type thread token. We went into that in the last lecture when I introduced state machines. So the thread token mechanism ensures that it's possible to find the correct UTXO that actually holds the state for the state machine in question. As I explained many times, validation in Cardano only happens when you try to spend a UTXO, not when you create one. So anybody can create a UTXO at any address with any data, any value that's completely unregulated. So at the address of a given token sale, there could be many UTXOs. And to identify the one that we actually care about, the one that actually contains the state of the state machine, we use this thread token, which is basically just a glorified NFT.
but this type comes from the library that deals with state machines.
And as redeemer, I provide exactly the operations we saw in the diagram. So set price to a new value. This is the token price in Loveless. Add tokens, where the argument gives the amount of tokens to add. Buy tokens, where the argument gives the amount of tokens to buy. And finally withdraw. This is actually like best practice to just give integer arguments because now it's not clear which is which. So in this case, the first one is supposed to be how many tokens to withdraw, and the second one, how many Loveless to withdraw. Then I have my helper function again. Lovelesses that given a value extracts the amount of Lovelesses in there. I also used that in last week's code, I believe. And now the transition function of the state machine. So the first argument is the parameter. And then recall we get the state. And in this case for datum, we will use integer. As I mentioned before, the price of the token and the redeemer. And then we must return a maybe constraint state. So we return nothing if the corresponding transition is illegal and just something if it's not. And then we must provide the constraints and the new state. And recall the state contains the datum and the value. So similar to last time, I split this given state into the value and the datum, and then I have the redeemer. So I pattern match on these triples in this case statement. And now I simply go through the 4 transitions.
The first case I'm considering is set price. So the seller wants to set the price to the new value P. I only allow that when the price is non-negative. And in that case, the transition is allowed if the transaction has been signed by the seller. And what about the new state? Well, the new datum should be P, the value given here in the redeemer. And the value shouldn't change. So the V is the old value. I should mention that the signature of must be signed by has changed. It's actually now better or more logical. In the past, we had to unwrap this payment pub key hash to get the underlying pub key hash. And that was always a bit annoying and also a bit inconsistent. So this seems to have changed now. So now this must be signed by does take a payment pub key hash, no longer a pub key hash.
The second transition is add tokens. And here I demand that the amount of tokens to add is positive. So not negative and also not 0. And in that case, there is no constraint. I could, of course, have put as constraint that it must be added by the seller. But the way I see it, I mean, this contract is created by the seller. The seller will set up the state machine and create the UTXO in the first place. So everything is written from the point of view of the seller. And the seller, he does care that only he can change the price. Otherwise, a buyer could set a lower price and then buy. So obviously the seller wants to be the only one that can change the price. However, if somebody so feels and wants to donate tokens to this contract, then the seller doesn't mind. Therefore, from the point of view of the seller, there doesn't have to be a requirement that he must sign that, as long as N is positive. So if somebody adds tokens to this contract, then the seller doesn't forbid it. Of course, in reality, probably nobody ever will, but there's no reason for the seller to allow that. That's why, in this case, no constraint is needed. And the new state, well, the price doesn't change, but the value changes by this amount of tokens. So it's the old value plus the value of the tokens that are added. So with asset class value token and this N I get the value of adding n tokens. Third case is buy tokens. Again, there is no constraint. Anybody can buy tokens. There's no additional constraint on the transaction. And the new state, the price again doesn't change. And the value changes. So we have the original value. We subtract the amount of tokens that are bought, which, by the way, is again a positive number. So you can only buy a positive number of tokens. And we also add the price. And the price is just the Loveless value of the amount of tokens times the current price, which is this P. Finally, we have the withdraw operation. So n tokens L Loveless. So we insist that both amounts are greater or equal 0. One of them could be 0. Maybe I should have forbidden that both are 0, but it also doesn't really matter. Then simply nothing will happen. In this case, that does have to be signed by the seller, because only the seller wants to be allowed to withdraw from the contract. And the new state, again, the price doesn't change. And the new value is, well, the old value V minus the n tokens that are taken out minus the L Loveless that are taken out. So minus, that's why I have the negate here. And that's all. All other transitions are illegal. So in all other cases, I return nothing in the transition function. Now that we have the transition function, we can easily define our state machine. And in this case, we can use a smart constructor called makeStateMachine. And the reason is, last time we had to use the actual constructor of the state machine because there was one check to check that the commitment, the hash, agreed with the actual choice. That was something we couldn't express as a constraint. But normally you can express everything as a constraint. And then you can use the smart constructor. That just takes 3 arguments. So the first is the thread token, or maybe the thread token, which we have from our token sale type. Then the transition function, which we just defined. And finally, the function that determines whether states are final or not. And in our case, we don't have a final state, so none of the states is final. So we can use the constant function that always returns false. So the idea is that once this token sale state machine has been started, it will run forever. There's no operation to stop it again. So once the UTXO is there at the state machine address, at the token sale address, it will always be there. You can't remove it again. And that's it. So this gives us our state machine. And then there's the usual boilerplate. So we can turn the state machine into a validator function like we saw last time. And then we get our typed validator with the usual template Haskell. And from that we get the validator and the address. And we can also, as we saw last time, easily define the state machine client, which, if you recall, is used to interact with the state machine from off-chain code from the wallet. So the client allows you to start the state machine and step the state machine, make a transition.
The next piece here, this TS-COF IDX, which stands for coverage index, is something new that we haven't seen before. And that is related, as the name suggests, to getting coverage information for tests. So I'll ignore this for now and come back to it later. But the way you get this coverage index is you take a piece of Plutus code. So in this case, we take our make TS validator and compile it. And then there's a function called get conf IDX.
Then I need one helper function that's also similar to last time because I want to use these operations from the state machine library, but they all use their own custom error type, some SM contract error. And I want to stick with text as error messages. So again, I use map error and then show and pack an SM contract error to convert it to text.
Now let's look at the off-chain code. So the first function I have here I call it start TS, start token sale, and it takes one parameter and doesn't have a result, but it uses this writer functionality with last token sale. So let's look at it. First, I ask for my own payment pub key hash. Then I use the get thread token function that we discussed in the last lecture, get a thread token, and I have to use this map error sm function that I just explained to convert the error to text. So with these two pieces of information, the public key hash and the thread token, I can define a value of type token sale. So the seller is given by my own public key hash. The token was passed in as a parameter to this function, and I now also have the thread token. And with that in place, I can call the TS client function to define a state machine client, and I can call run initialize with this client, and I have to give the initial state, so call that's of type integer and corresponds to the initial price, so that I just set to 0, and I must say how much value to put into this initial UTXO, and I just don't put anything in there. And again, I have to use map error to convert the error messages to type text. Now I tell the TS value so that other contracts are able to look that up and then refer to this token sale. And finally, I just log a message. Now I have simple functions corresponding to the various actions, set price, add token, buy token, and withdraw. And those are just one-liners. This is now again very nice, a very nice demonstration of the beauty of this state machine mechanism, because all I have to do is use this run step and provide the client and the action I want to take. And every case, I have to use this map error sm to convert the error messages accordingly. So I can set the price by doing this with the set price action, add tokens using the add token action, buy tokens using the buy tokens action, and withdraw using the withdraw action. So this is now really beautifully short, much simpler than it would be if we didn't use state machines. And it's guaranteed to be in sync with the on-chain code. So it's guaranteed to create transactions that will then be valid and will pass validation. Now I can bundle everything up. So I define two schemas, one to start the token sale and then one to use it. So the start schema only has one endpoint that I call start. And recall the start_ts function took an asset class as argument, but it's easier from the UI point of view to split that up like I did last time into a pair of currency symbol and token name. And then for use, we again have our 4 actions. So set price takes the new price as an argument, add tokens takes the amount of tokens to add as an argument, buy tokens takes the amount of tokens to buy as an argument, and finally withdraw takes a pair of integers, how many tokens I want to withdraw, how many loveless I want to withdraw. Then I can define start endpoint and use endpoint that now use these schemas, and they basically just use the functions I defined before, just incorporating these endpoints now. So to start, I use this start endpoint and then just call my start TS function before I bundle the pair of currency symbol and token name up into an asset class. And I also handle errors by just logging the error. So if an error happens in this function, the error should just be logged and the contract should continue. And I use forever. So that means once this is done, it will start again. So I can start arbitrarily many token sales with this. Then the use endpoint bundles up these 4 actions, and it will forever select one of those 4 actions, and all of those are implemented in the obvious way by just calling the functions we defined earlier: set price, add token, buy token, and withdraw. So the only wrinkle here is that I use uncurry. So recall the withdraw function took 2 arguments, type integer and integer, whereas the endpoint takes a pair of integers. And that's exactly what uncurry does. So the endpoint delivers a pair of integers, and then uncurry enables us to use this pair of integers with the withdraw function. So converts it into a call to a function with 2 arguments.
If we look at uncurry, the signature, you see it takes a function with 2 parameters, a and b, and turns it into a function that takes a and b as a tuple. So for example, if as function we take plus addition, which takes 2 a's, then if we have uncurry plus, that is now a function with 1 parameter, a tuple. So for example, we can do uncurry 3, let's specify it's an int, and 4, and we get 7 as expected.
And that's it. That's the code for our token sale.
In order to try it out, let's first use the emulator as we did before. So I define a run my trace function that again uses run emulator trace.io prime with a custom emulator configuration and my trace. We'll get to my trace in a minute. Let's first look at the custom emulator configuration, where again I specify an initial distribution that doesn't give only ADA to the wallets but also some other token. So the idea is every wallet gets 1000 ADA, and in addition to that 1000 tokens, where token is just arbitrary currency symbol AA and token name capital A. These underscores make it easier to read large numbers, and they are provided by a extension, GHT extension, that's called numeric underscores. So we'll only use 3 wallets, 1, 2, 3, and each of them will have 1000 ADA and 1000 of these tokens. Now for the trace, first we activate the start endpoint for wallet 1. So wallet 1 will be the one running the token sale, owning the token sale. And as parameters, we give our currency and name that we defined here, so the AA and the A, so that will be the token that can be sold. Then we just wait for 5 slots to give this enough time to start the state machine, and we ask for the observable state, which, if you recall, should be the token sale value that has been started. And then there are 2 possibilities: that this M is nothing, in which case the token sale hasn't started yet or something went wrong, so we log an error message. And in the good case, the one we expect, we do get our TS of type token sale. So we just log a message, and now we can start the use endpoint. Remember, the use endpoints are parameterized by this TS value. So we need to know the TS in order to start the use endpoints. So we start them on all 3 wallets, 1, 2, 3, and then we call various endpoints. So first, wallet 1 sets the price to 1 ADA. We wait for 5 slots. Now wallet 1 adds 100 tokens to the token sale UTXO. We wait another 5 slots. Now wallet 2 buys 20 tokens. And because the price at the moment is 1 ADA, that should cost 20 ADA. We wait another 5 slots. Wallet 3 buys 5 tokens, which should cost 5 ADA because the price is still 1 ADA. We wait again, and finally wallet 1 withdraws 40 tokens and 10 ADA. So originally there were 100 tokens, 25 have been bought, that leaves 75, 40 are withdrawn, so 35 should be left. And initially there were no ADA, but wallet 2 paid 20 and wallet 3 paid 5, makes 25. So if we withdraw 10, then 15 should be left.
So let's briefly try this in the REPL. But before we do that, let me just show you the Cabal file. And actually, the trace I just showed you is in a module called spec.trace, which is not in the main library of the package. Rather, it's in a so-called test suite. Test suites in Cabal are set up very similar to executables. So the parameters you have to specify are very similar. In particular, you give a main file that needs a main function of type IO, and you can specify the source directory. And so that's very similar to how you also set up an executable in the Cabal file. The only difference is this type here, this exit code standard IO 1.0. That tells Cabal how to actually execute tests, and we can do that later. The point, however, is if we want to start a REPL for something that's not the main library of the package, you have to do that slightly differently. So normally we start the REPL just with Cabal REPL, but we can't do this now because we have this spec.trace, which is in a different stanza. It's in this test suite in this case. So the syntax for that is as follows. It's again Cabal REPL that now you need parameter, one parameter. So first it's the name of the package, and then colon. And now if it was an executable, it would be exe, and then the name of the executable. But in this case, it's a test suite. So it's colon test, another colon, and the name of the test suite. And this is called, as we see here, Plutus Pioneer Program Week 8 tests. So tests, so like this. And then the REPL will be started for this test suite instead. So now I can load the module. It's called spec trace. And now I'm there. I can execute run my trace. And we can check the results. So this first wallet here, wallet 2. So it bought 20 tokens. That seems to be correct. And the price was 1 ADA. So it has roughly 20 ADA less than the original 1,000. Wallet 3 bought 5 tokens, so now has 5 more, 1005, and roughly 5 ADA less the price for the tokens. And finally, wallet 1 put 100 into the token sale, but then withdrew 40 again, so ends up with 940. We did withdraw 10 ADA. However, we only have like 8 more, and the discrepancy of 2 is due to this min UTXO again. So in order to set up the token sale UTXO, we have to deposit this min ADA amount, which in the emulator trace is always set to 2 ADA. In reality, it will be slightly less, and it's also not a constant, as I explained before. It depends on the size of the UTXO. But that explains why we don't see 1010 ADA here, but only roughly 1008. Finally, this last thing here is the UTXO itself, the state machine, the token sale. So as we calculated before, we said 35 tokens should be left, which is correct. But we also said 15 ADA should be left. However, we see 17, and this discrepancy again, that's exactly this minimal deposit which was added in the beginning. We didn't explicitly mention that. which tells us that the state machine mechanism automatically takes care of that. So in the start token sale function, when that constructs a transaction, it will automatically add the required deposit of 2 ADA to the UTXO we create there.
So our contract seems to work, at least as far as the behavior with this trace is concerned. But in order to come to that conclusion, we had to execute it in the REPL and manually check the result, which of course you wouldn't want to do in a production environment. In a production environment, you want to have automatic tests, for example, unit tests. So we'll look at how to do that in Plutus next. This is actually the topic of today's lecture.